Welcome to today's explainer. Right away, I want you to picture a brutal, high-speed 90-second gauntlet. On one end, a massive plate of raw, warped, and honestly pretty rusty steel rolls in. But just a minute and a half later, it emerges completely transformed. We're talking perfectly flat, blindingly bright, and shielded with its microscopic layer of armor. It is entirely ready for the extreme precision demands of shipbuilding.
So today we're breaking down exactly what happens inside that 90-second gauntlet. There's actually a super common misconception that when raw steel arrives from the mill, you can just immediately start cutting and welding it. Oh, definitely not the case. Raw steel from the mill has deformations, it's already starting to rust, and it's covered in this hard, dark crust. Contrast that with what we actually need, perfectly flat, bright silver gray, and primed. Before any of the precision work can even start, the steel literally has to undergo a radical physical transformation.
All right, the first major enemy we have to deal with here is mill scale. See, when steel plates are manufactured at the mill, they go through a hot rolling process. Basically, they're squeezed between these massive rollers at incredibly high temperatures. And this extreme heat and pressure, it creates a hard, brittle oxide layer on the outside of the plate. That's the mill scale. If you try to paint over this stuff, the paint's just going to flake off eventually. And if you try to weld over it, man, it will completely ruin your weld quality. So yeah, this crust absolutely has to go.
But, surface crust isn't our only problem. We also have to ask, why do these massive, thick, seemingly solid steel plates arrive at the shipyard warped? I mean, it seems totally counterintuitive, right? Something that heavy and rigid just naturally curving and bending on its own? Well, the answer actually lies in the invisible forces trapped deep inside the metal itself.
Here's what happens. As that hot-rolled steel plate leaves the mill, it cools down, but it doesn't cool evenly. The outer surface cools much faster than the hot interior. And this differential cooling creates intense, locked-in residual stresses. These internal tensions literally cause the plate to spring slightly out of flat. And think about it. If you try to run precision computerized cutting or automated welding on a wavy plate, the geometry is going to fail completely. So we absolutely have to intervene.
Section 1. The mangles, flattening the steel. Okay, this first station sounds a bit like a medieval torture device, and honestly, the mechanical forces involved here are just staggering. In the industry, they call it the mangles. It's essentially a series of exceptionally heavy, counter-rotating rolls. The warped plate gets fed through, and the machine applies controlled bending in alternating directions. It's basically forcing the steel to bend back and forth, over and over again. It's kind of like intense physical rehab for the metal. It progressively works out all those locked-in residual stresses from the mill until the plate comes out completely flat, well within the required geometrical tolerances.
Section 2. Shot blasting. Removing mill scale and rust.
Right, so the plate is perfectly flat now, but it is still covered in that terrible mill scale and early rust. Now inside the shot blast machine, we aren't using chemicals or water to clean the steel. Nope, instead millions of tiny steel balls, literally metallic shot, are propelled mechanically. They just rain down onto the top and bottom surfaces of the plate at incredibly high velocities. The sheer physical impact of this steel rain literally shatters the brittle mill scale and entirely strips away any rust or surface contamination. It turns this dark, scaly plate into a beautiful, bright, silver-gray canvas.
But here's the really crucial point. The result is a clean, slightly rough surface profile. And that roughness, it's absolutely critical. Actually, we don't want the steel to be perfectly smooth like glass. No way! The violent impact of the shot leaves this microscopic, jagged texture. And we need that specific roughness because the next layers of protective coating need something to physically and mechanically grip onto so they can stay attached for the entire life of the ship.
But of course, solving one problem immediately creates another. We now have this beautifully clean, slightly rough, and highly reactive silver-gray plate. So what happens if you just leave that freshly blasted steel sitting unprotected in the salty, humid air of a typical shipyard?
Well, the answer is pretty grim. Freshly shot blasted steel will literally start flash rusting within hours. I mean it. You simply cannot blast a plate on a Monday and expect to weld it a month later. It would be completely ruined. It's a frantic race against time. And this fast-acting threat is exactly why the blast machine and the priming plant are always physically connected in one continuous, seamless production line.
Section 3. Prefabrication primer. The microscopic shield.
As soon as the steel leaves the blast machine, it enters the final stage of our gauntlet to get its armor. And this primer shield is astonishingly thin. We're talking just 15 to 25 micrometers. To put that into perspective for you, a human hair is about 70 micrometers thick. That's a crazy contrast, right? You have thousands of tons of massive, heavy industrial steel, relying entirely on this microscopic shield to save it from environmental ruin before the ship is even built. This coating is often called shop primer or weld-through primer, and its sole purpose is temporary protection. It is highly engineered to withstand the abuse of cutting, structural assembly, and the erection of giant ship blocks over several months. But, really important note here, this is completely different from the final, thick, glossy paint system the ship is going to wear when it eventually goes out to sea.
Notice how we called it weld-through primer? It's specially formulated so shipbuilders can weld directly over it. Think about it. If you tried to run a high-temperature welding arc through regular house paint, the paint would just burn up, produce trapped gases, and create these tiny, strength-reducing voids in the metal. That's a critical defect known as porosity. But this special primer allows the weld to penetrate cleanly without compromising the structural integrity of the ship at all.
And here is how fast this protective phase happens. The plate exits the shot blast machine, it's still warm from all those kinetic impacts, and it's highly chemically reactive, and it instantly passes into an airless spray booth. The microscopic primer is applied uniformly across both faces at the exact same time. And because the steel is still warm, the primer dries within minutes. The whole shebang, from a warped, rusty plate to a flat, primed canvas, takes less than 5 minutes.
This whole sequence just brilliantly illustrates the journey. We've got 3 main enemies, and 3 highly engineered machines built specifically to defeat them. Locked in residual stress and warping, beaten by the alternating bends of the mangles. Mill scale and surface rust, destroyed by the high-velocity kinetic impacts of shot blasting. And that immediate threat of flash rust, completely neutralized by the microscopic layer of prefabrication primer. It really is a perfectly synchronized system.
So, at the end of the line, the steel is geometrically true, surface clean, and completely shielded. It has officially survived its intense physical rehab. It's no longer just some flawed raw material straight from a mill. It is now precision stock, fully designated and prepared to become the highly stressed structural skeleton of a massive ocean-going vessel.
Which leaves us with this final, burning question. We've managed the logistics, we've flattened the warping, we've blasted the scale, and we've applied our microscopic shield. Now that the steel is perfectly true and clean, is it finally ready to face the extreme fires of the cutting floor? The next step in actually building this ship involves precision thermal cutting, using oxyfuel flames, plasma arcs, and even lasers. But we're going to have to explore that explosive shaping process next time. Thanks for joining me on this explainer.